Looking at this example, there are a lot of things going on. I'm going to start by just splitting this page in half because we are asked for a lot of material. We want to find critical numbers, inflection points, relative max and min, increasing, decreasing, and concave up and concave down. So I'm going to split this up according to which derivative that we are working with. So critical numbers, that is what makes the first derivative 0. Relative max and relative min come from the sign chart of a first derivative as well as increasing and decreasing. Everything else is second derivative. So inflection points is what makes a second derivative 0 that also has a change in concavity. So starting with the first derivative, we're going to do our 2 steps. We have to take the derivative of this and set it equal to 0. So I'm going to bring down that power. I'm going to have 3x squared. Bring down the power again. 12 times 2 is going to give me 24x. Derivative of 5 is just 0. So I'm going to take that first derivative, set it equal to 0. It has an x squared and an x in it, so I'm going to have to factor this. So I'm going to pull out a 3x as my greatest common factor. It's a binomial. It's not a difference of 2 squares, so I'm going to pull out a 3x. My greatest common factor is my biggest number and my least power of x. So 3x times x will give me 3x squared, and 3x times a positive 8 is going to give me that positive 24x. So I want to figure out these 2 things can only multiply to be 0 as long as one of them is 0. So I want to see, can anything make 3x 0? Yes. 3 times 0 would give me 0. And can anything make x plus 8 0? Yes, if x is negative 8. Which for each of these, you could divide by 3 to figure that one out or subtract 8 to solve that one if you need to. If you can't just see it right off the bat, that's fine. So we have 2 critical numbers automatically. Remember, critical numbers, they don't require you to have a change in the sign chart. That's only inflection points. And as long as they make the derivative 0, that first derivative 0, and make the can go into the original function, then they are critical numbers. So because this original function is a polynomial, I'm not worried about not being able to plug those in. And nothing's going to make this polynomial divide by 0 or anything like that. So we have our 2 critical numbers, and we're just going to make a sign chart to find the rest of the first derivative information. So I want to put these 2 numbers on here. Negative 8 comes first, and then 0. These both make the derivative 0. Those are my critical numbers, the only place where I could possibly switch from increasing to decreasing, and the only place where I could possibly have relative max and relative min. I can choose any number to the left and right of these. So to the left of negative 8, I could plug in negative 10 into the derivative. So 3 times negative 10 is going to give me a negative. Negative 10 plus 8 is going to be a negative. So 2 negatives are going to multiply to be a positive. So this function starts off as increasing. I'm going to do that same thing again with a number between negative 8 and 0. So maybe I'll choose negative 1. 3 times negative 1 is going to be a negative. And then negative 1 plus 8 is going to be a positive. So I'll have a negative times a positive on the interval, which is going to give me a negative. First derivative ruled, negative means decreasing. So at negative 8, I switch from increasing to a 0 derivative at the critical number, a soft peak, to decreasing. So I have a relative max here, by the way. After 0, I can plug in anything that I want to as my test value. Maybe I'll plug in positive 10. So 3 times 10 is going to give me a positive 30. 10 plus 8 is going to be a positive number as well. So I'm going to have a positive times a positive, which is positive. So I switch and I'm back to increasing there. So at 0, I went from decreasing to increasing. And then I went through a critical number, which is a soft peak on the graph. So I have a relative min there. So I can fill out this first derivative information. For increasing, I'm increasing on this interval here and this interval over here. Remember, we only switch at critical numbers. So I'd write that first interval as negative infinity to negative 8, union 0 to infinity. Don't use any random test values in here. And then I'm decreasing between my two critical numbers. So between -8 and 0, I'm decreasing. Now I need to probably grab my calculator because I need to find some points here. So I'm going to have to plug into the original function finally. Always use a derivative on a sign chart. If you're looking for increasing and decreasing, use the first derivative. If you're looking for concave up and concave down, use the second derivative. The only time you plug into the original function is to find the y values of a point. So my max point is going to be at -8. That's where I had the sign change increasing to decreasing. So -8 comma, I'm going to plug into this original function in parentheses -8 cubed plus 12 parentheses -8 squared plus 5, and the y value there is 261. And then I had a minimum at my other critical number, 0. So I'm plugging 0 into the original function, which is nice and simple. Don't even need a calculator for that. I just get 5. So there we just did all of the work with the first derivative. Now we're going to do the same exact 2 steps, but get a different interpretation because we're going to use the second derivative. So second derivative world is all about concavity and inflection points. Let's see what we have going on. You might be able to take a guess by looking at this sketch here that, hey, maybe there is an inflection point because it looks like we switch from concave down to concave up. So these should match because they're modeling the same function. So let's see if we get something that looks similar to what we had as our sketch for the first derivative. So we're going to take the second derivative. I'm not going to use the factored form because then I'd have to use the product rule. I'm going to look right here at this first derivative, bring down the power. 3 times 2 is going to be 6x. Derivative of 24x is 24. I'm going to set this equal to 0. And it's a lot simpler because I don't have to factor. I don't have an x squared and an x, so I do not have to factor. I can just subtract 24 to try to get x by itself. So I'd have 6x equals -24. And then I can just divide both sides by 6. So x is going to be -24 divided by 6. It might not be a whole number, which is fine for these, but it actually does work out to be a -4. Just keep in mind, sometimes it is a fraction, and that's okay. That's our possible inflection point. It's not necessarily an inflection point unless we have the sign change on our chart. So I'm going to put -4 on here. And this is special. This is what makes the second derivative 0. And it's only called an inflection point if we change concavity. So I'm going to test any number to the left of -4, maybe -10. And I'm plugging into the second derivative. So I'm going to do 6 times -10 plus 24. So I'll have -60 plus 24, which is still going to be negative. So at first, this graph must be concave down. It might continue to be concave down, might switch. Looking at this sketch, it looks like it's going to switch, but let's check by plugging in any random test value to the right of -4. I always like to plug in 0 when I can. So I'm going to do 6 times 0 plus 24, which is going to be 0 plus 24, which is positive. So I do switch to being concave up, which means I have this inflection point here where it looks like it's between the two concavities. Our graphs match. We have our inflection point, or point of inflection, and we see that they do match. It is increasing to decreasing to increasing on both graphs, which makes sense because they're both trying to see what x cubed plus 12x squared plus 5 looks like without ever having a picture of the graph. So now we can interpret this second derivative information. So concave up is going to be from -4 to infinity. Don't use your random test value of 0. Concave down is before -4, so -infinity to -4. And then I just need to grab my calculator because I need to find a point, which means I need to know the y value. This is the only time you plug into the original function. In parentheses, -4 cubed plus 12 parentheses, -4 squared plus 5. I'm getting 133. So now we have a very good idea of what this graph looks like. We could graph our points. If we wanted to draw a little sketch of this, we would graph our points first. So we'd say we have a relative max at -8, 261. This is a very rough sketch. And then we have our inflection point at -4, 133, so like halfway to there. And then our relative min is at 0.5, just barely above the x-axis. And we go from increasing to decreasing to increasing, and we have this point of inflection that looks like it's between the two concavities. So you have a very good idea of what the graph looks like. I could obviously put more effort in and draw it a little bit better, but that is what x cubed plus 12x squared plus 5 looks like.